So for this problem, you're going to get to show off your angular momentum knowledge. So to start with, we're going to calculate some moments of inertia. See if you can go through and figure out how to calculate each of these correctly. So for the first one, calculate the moment of inertia of someone's ring being spun around its diameter. So the ring, you can model a ring as just a circle. It's hollow on the inside, all the mass is on the outside. And it's spinning around a vertical axis going through it. We'll say that is a mass, 50 grams, and a radius of 1 centimeter. So see what the moment of inertia is of the spinning ring. For the second one, imagine that we have a sphere transfixed by a rod, and it's being spun around an axis perpendicular to that of the rod, and the rod's the same distance on both sides. So say the rod is distance L on both sides, and the sphere is radius R. And we'll say this is like a weight. So the sphere is going to be 20 kilograms, and the bar is going to be 10 kilograms. So see if you can calculate what it's going to be. And actually to make things easier for you, we're going to say that the bar is 12 kilograms, and the sphere is solid. And then one final one. Imagine a dumbbell is being spun around. So it's two solid point weights on the end, each of which are 10 kilograms. And then it's being spun about an axis 2/3 of the way down. So we'll say that there's 60 centimeters of rod on this side and 20 centimeters on this side. And then the rod itself weighs 20 kilograms. Oh, and for the second one I forgot to mention, the radius on the first one is 10 centimeters, and the radius on the second one is 20 centimeters. So good luck. Let's start with the first one. The first one's relatively easy. All we have to do is just plug in the appropriate numbers for the appropriate constants. It's a solid sphere, so I equals 2/5 mr squared. Sorry, not a solid sphere, it's a hollow ring. I'm not sure how I got a solid sphere from that. It's a hollow ring, and it's hoop about diameter. So it's the second ring type. So I equals 1/2 mr squared. So then we can say 1/2 mass of 50 grams, radius of 1 centimeter, that's squared. So we're left with 25 grams centimeters squared. It's important to keep units here because for different problems we have different units. Some will be in kilograms meters squared or kilograms centimeters squared. So pay attention to your units. Let's go on to the second one now. The second one's a little scarier. We have to superimpose two separate moment of inertia equations over each other. But don't worry, that's actually an equation that sounds much scarier than it really is. All that means we have to add two together. And for this one, we have a solid sphere with an axle running through it. The solid sphere has a mass of 20 kilograms. The axle has a mass of 10 kilograms. So 12 kilograms. And then the radius is 10 centimeters, and the axle is 20 centimeters in one direction. So let's go through and try to calculate this. We'll do it step by step, very carefully. Solid sphere. I equals 2/5 mr squared. 2/5, mass of 20 kilograms, radius of 10 centimeters squared. So we do the math. 2 times 20 is 40, divided by 5 is 8. So that's 8 times 100, because that's 10 squared. So as a result, we're left with 800 kilograms centimeters squared. And that's significantly bigger than our previous answer. Our previous answer was 25 grams centimeters squared. This is kilograms centimeters squared. And now let's move on to our third and final problem. For the third and final one, it's 2 point masses. And if you remember from the lecture, a point mass... Oh, sorry. That's only for the first part. Now we need to move on to the second part. So the second part, it's a bar. And the bar has a length of 20 centimeters in one direction, which is 40 centimeters overall. And it has a mass of 10 kilograms. Sorry, 12 kilograms. I keep misreading that one. And now we need the equation. We know the equation is I equals 1/12 mr squared. So that's 1/12 times 12, and that's why it was 12, times 40 centimeters squared. So let's do the math out here. 12 times 12 cancels out. And we're left with 40 squared, or 1,600. And the distance was in centimeters. And the mass was in kilograms. That's kilograms, centimeters squared. And we add this to our previous result of 800 kilograms, centimeters squared. And it's the same unit, so we can just add it together. We get 2,400 kilograms, centimeters squared, which happens to be 2.24 kilograms, meters squared. So either of those results are correct. Just take whichever one is easier for you to understand. And now let's move on to the final one. Looking back at the previous video, we remember the point masses. Their moment of inertia is mr squared. And the radius of these point masses, 20 centimeters and 60 centimeters. And both of these point masses has a mass of 10 kilograms and are mounted on a 20 kilogram rod. So now we need to try to figure out how to solve this. We're going to solve it as four separate things. One point that's 60 centimeters away from the center. One point that's 20 centimeters from the center. One point, and then a bar, and then two separate bars. We can't do it as one bar like we did last time because it's not rotating about the center. So it's two separate bars. And because it's 60 centimeters and 20 centimeters, 3/4 of the mass is going to be on the longer side because the total length of 80, and so 60 over 80 equals 3/4. And 3/4 of 20 is 15, and so the other side is going to be left with 5. And that makes sense because they add together to be 20, which is the total mass. So now let's do the math here. This is a bit of a long expression, so let's go through it step by step. This part is just a left-hand mass. It's 10 kilograms, 60 centimeters squared. This is the right-hand mass. This represents the longer portion of the bar. For a bar being rotated around its end, it's not 1/12, but 1/3. And then this is the same for the other one. We put in the right masses. We put in 15 kilograms and actually 5 kilograms over here. And then we put in the corresponding lengths. So now we need to do the math out. And I'll solve it out. You can solve it out with a calculator or try to write it out. Shouldn't be too hard. The first two add up to an even 40,000 kilograms, centimeters squared. And the second two add up 18,666.6 repeating. So all this adds up to 58.6666 repeating kilograms, centimeters squared. And since 10,000 centimeters squared equals 1 meter squared, we can divide through by 10,000 and instead get 5.86 kilograms, meters squared is the moment of inertia of this spinning dumbbell. So hopefully that made sense to you. If not, go back and rewatch it. And if you got that, you're ready to move on to actually doing angular momentum with rotating objects.